Thanks very much. So yes, first of all, Mark sends his apologies. He was called to a meeting in London that he couldn't get out of, so he had to fly off at 6 o'clock this morning to go to London. Thankfully, I was a work package leader on CRESTA, so I know something about the project and I could step in at short notice. Okay, so the CRESTA project is the only one of the projects being presented today that's actually finished. So we finished at the end of December last year. We ran for 39 months. And the CRESTA acronym stands for Collaborative Research into Exascale Systemware, Tools and Applications. It was quite a large project like Deep and Mont Blanc as well, so 12 million euro. In terms of our partners, it was a mix of European HPC centres, so EPC in Edinburgh, HLRS in Stuttgart, CSC in Finland, and KTH in Sweden. We had one of the core partners was Cray as our hardware supplier. We had world-leading tools providers, TUD with their Vampire tool and Must tool, and Alinea that brought DDT and MAP into the project. But then importantly, we also had quite a few application owners and application specialists. So Åbo Academy and University, Jyväskylä University in Finland, UCL and in London, ECMWF, the European Centre for Medium Range Weather Forecast, also in the UK, the École Centrale de Paris in France, and then DLR, we already heard about today as well, in Germany, KTH again in Stockholm, and UStutt, University of Stuttgart. So if you look at our geographical location, we're very Northern European focused, so we didn't have anybody south of Paris, unfortunately, this project. So, we've heard lots of talks about hardware for the Exascale, we've heard talks about programming models for the Exascale and so on, and CRESTA, fits in quite nicely together with Deep and Mont Blanc. So the Exascale challenge from CRESTA's point of view is both a hardware and a software challenge. Okay? So looking at what we currently have in terms of the technology roadmap that the vendors have presented last week here as well, it just seems impossible to build anything below 50 megawatts. And in fact, this morning I heard somebody talk about if you do some calculations, actually you're looking at 150 megawatts, not 50. So, if you have GPUs and ZN5s and all the traditional processors and memory hierarchies and so on that you have now, we can't really see how at the moment you could get to below 20 megawatts with this. And so the solution is, we have currently these systems with very fast processors and fairly slow memory and bottleneck and interconnect. We really need to rebalance the systems that we have. So we want smaller, simpler processes, Mont Blanc's approach with the very simple cores. But you also want much simpler memory hierarchies. And you want better communication links so that your system doesn't have this huge imbalance that they currently have. But if you do this, you hugely increase the amount of parallelism you have and you have to cope with. So if you take today's leader, Tianhe 2, and if you scale it up to the Exascale, you end up with 92 million cores and the smidgen of 526 megawatts to power it. So that's obviously not the solution we can go down. So if you slow down your cores and you balance your machine better, CRESTA's thoughts are that you're around 500 million to 1 billion parallel threads. But this means that hardware, as we're going forward, as we're going towards Exascale, is really leaving software behind. We just don't know how we can compute that level of parallelism. And the algorithms that we compute with are simply not designed to cope with this amount of parallelism. If you look back, actually just the other day I looked back and when finite element methods was first introduced, and it's a long time ago. It's 40 years ago now, and computers have changed somewhat. So, this parallelism is just a matter of implementation is unfortunately a mindset that is very common when you speak to people. Just parallelize it. It'll just do. And there's often a huge amount of duplication of effort going on. People are very loath to reuse good code, and because code development then often ends up being a very personal thing. change is a very difficult thing to instigate. And this is the social point we talked about earlier. People don't like change at the best of times, but when it's scientific change, they don't like it at all. And so we're a bit of a tipping point at the moment. So, we can't just continue rewriting applications a little bit here and a little bit there to make them scale a little bit further, because we're just going to get to the end where we can't do this any longer. And we need some fundamental changes in the algorithms. This, not just an exascale problem, it's a petascale problem. Some changes in the past go from terascale to petascale. Well, it's worked just fine, just making a few adjustments here and there. But a lot of codes today, the number of codes that truly scale to the petascale, well, very few. If we remove QCD from the equation, very, very few. Okay. Plus, skills gap is huge. If you ever try to hire HPC experts, you know how difficult it is. And tools are very difficult as well. So, software and how we model and simulate the actual exascale problems that we want to solve, those, for us, remain the key challenges. So CRESTA looked at both software and systemware. So sort of a two-strand problem. And systemware here encompasses everything from, compilers, runtime system, batch systems, everything that sits just above the hardware and between the application, things that allow you to actually run the application on the system. And now the software itself, we had a set of Codesign applications, and we had all the code owners or key players with the code in the project as well. And the Codesign word has been mentioned a number of times. This was definitely at the heart of the project. So these co-design applications were there to guide the research, guide the process of what we're going to do, and feedback to the systemware development process, and the systemware development process fed back into the application development process, and so on. So there was quite a cyclical process going on, talking, the application owners talking to the systemware developers, and vice versa. And we looked at both incremental and disruptive solutions. So we believe that incremental changes are necessary, but so are disruptive solutions. There comes a point where you just have to take a leap of faith and just go for it, because you won't be able to just step towards a solution. That is particularly true for applications that are just reaching the limit of the scalability in terms of the mathematics they employ. And those sort of incremental solutions have, in the past helped code scale to terascale and petascale, but it's much less likely this to be the case for the exascale as well. The project was committed to open source, so a lot of our software is online on the CRESTA GitHub, and a lot of our work's been published in white papers and case studies, which are available on the website. So I've already talked about this incremental approach. So there's a lot of, iterative optimization and performance modeling and so on. And, this is about achieving the maximum performance you can with the tools you have right now. Whereas disruptive approach, it's important to understand what your major bottleneck is and how you can move away from that bottleneck, not just by stepping up, a small step, but by just basically rejecting the solution you have and just start again. But, as I said already, humans don't like change. A lot of the codes have been developed, for 20 years or more. Getting the code owners to, agree to huge changes is very, very difficult. Disruptive change is difficult, complex, both from scientifically and from the implementation point of view. It's costly. It's unlikely that your PhD student will be able to just do it in addition to all the other work. And costly, it's very time-consuming as well. So it can take many man-years of effort to implement disruptive changes. But in CRESTA, we have shown that there are situations where it's just needed, where you will just need to invest the money and push these disruptive changes. Two examples I'm going to come back to are IFS and OpenFlow. And getting people to think disruptively is really, really difficult. We had, as part of CRESTA, we ran these disruptive technology meetings where we all got together and all wanted to think disruptive thoughts. And it's hard, it's really hard, mainly because we all know what we can't do. So getting beyond the bit where you think, well, we know that's impossible. So, okay, just forget it's impossible. Just start again, just think again. That's really, really hard. So CRESTA is not a hardware project. And we've been criticized that our co-design approach is not really co-design because there's no hardware, so how can it be co-design? But you don't, our thinking was that you don't really need the hardware to think about what the hardware will be. So even the hardware projects don't have exascale machines. They have ideas of what it will be. And so, you don't have to build it, okay? So when we worked, we assumed massive parallelism, okay, 100 million threads, parallel threads or more, okay? We assumed that most likely it's going to be heterogeneous threads, heavyweight threads, lightweight threads, CPU plus accelerator, maybe plus something else, maybe plus an FPGA, although we didn't go that way, I have to say. Multi-layer memory, well, we already have that. I/O hierarchies, non-uniform networks, non-uniform performance, okay? So, there is some influence back from our work into hardware design. So we work with Cray very closely. And I'm sure, other vendors who have read our publications will also take our assumption and the work that we've done into account when it comes to hardware design. A couple of comments on hardware developments. So slowly we're beginning to see how vendors are going to approach the exascale. There's there have not been any major announcements, really, apart from the China 2 announcement that the Chinese are developing their own accelerators. But there's not been anything major the last few days, okay? But we believe a key period in hardware development will be about 2017 to 2019, something like that. It currently feels a bit of a lull before the storm. The number one system hasn't changed in a while. Things are a little bit quiet, but it's about to change, we feel. There have been some comments that CRESTA is overestimating how many parallel threads there will be. So we've been saying 500 million. Some people have said that is far too much. It won't be that. There will be more heavyweight threads, and there will be many fewer than that. Don't worry about having to use 500 million threads. We feel it's better to overestimate than to underestimate in this case. But another challenge is turning all these developments at the low level to, a system at scale. I mean, I guess that's something that Mont Blanc has noticed. You have a node, new technology, everything's great. Scaling the machine up, that's much, much harder than, just saying, oh, look at this node, isn't it amazing? Power efficient, performant, everything. Okay, we'll just multiply that up to the exascale. It's not that simple. And very few vendors exist today that can build reliable large systems, okay? So there is a real need for very in-depth engagement between application system and hardware as well. Okay, so this workshop is called Europe on the Road to Exascale. So where are we? This call text is from the work program that funded the first Deep and the first Mont Blanc and CRESTA as well. I mean, if you look at the text here, it's a very optimistic text. Okay, it says, extreme performance, 100 petaflops in 2014, okay. Exascale by 2020, right. So we're 2015, and the largest machine in the world, which hasn't changed in a year and a half, I think, right? We're at 34 petaflops. 100 petaflops probably will be breached in, 2016, maybe supercomputing 2016. So the tail end of 2016, maybe early 2017. So we're a little bit behind here. And here, people say 2020. Okay, last supercomputing is 2022. This ISC for 2024. So, it's the distance. It's good for us, right? Because it's lots of work to do. But it's sort of moving away with us. It's like pushing the goal ahead of us. And I mean, Europe, 6.3 petaflops, right? It's a long way down the road. Some challenges of the Exascale. Okay, this has been mentioned already, but I'll go over it again. Power. Okay. The only country who has a published plan for close to the Exascale, they wouldn't say Exascale, is Japan. They're targeting 2020, but that was a few months ago. This was discussed. Whether it's still true, I don't know. But the power consumption of that machine was about 50 to 60 megawatts. So at the current price that we pay for electricity at EPCC, that would cost us 70 million euros every year, which is a lot for a university or even a government. Plus, we're currently at 8 megawatts. It's a large data center. We can see how we get up to 20 megawatts of building our own power station, as you do. But, going beyond that, we're one of the largest data centers in the UK, and we're finding it's very, very difficult. Parallelism, another challenge. So we've shown in CRESTA that parallelism really is an issue for systemware as well as for software applications. And we do need a lot more innovation in the algorithm side. Plus, we need to plan. So we can't just expect our software to, change overnight. It needs to be a community effort. Everybody needs to plug a lot of effort into this. People have to think hard about how they want to solve the problems. And this is expensive. But we need to decide as a community, and I guess convince our governments as well, that this is an expense that's worth paying. So our co-design applications that we use in this process, Elmfire is a plasma code. We use it to simulate the behavior of plasmas inside a fusion reactor. What we did here is we completely rewrote the way that the main decomposition was done. So it's a completely rewrite. It's a 3D decomposition, and we also worked on the visualization of the plasmas. GROMACS, a lot of people know, a very popular molecular dynamics package. The work we did here was to, in general, improve the implementation. There's a lot of tidy up, a lot of code reorganization for task parallelism, but also a framework that allows ensemble modeling. HEMALB is a code that is used for blood flow modeling, so it models the blood through arteries to detect aneurysms. So it's used for clinical planning, that kind of thing. And here was the physics was changed, and the performance and scaling of the code was looked into as well as some pre- and post-processing work. IFS, this is the integrated forecast system from the ECMWF, so the European Centre for Medium-Range Weather Forecast. They're the guys that do 4 weeks to 3 months forecast for the whole of Europe. A lot of interesting work was done here. This is, I believe, the only code we've done any PGAS work. So we used CoRay Fortran inside an OpenMP parallel loop. And the code is MPI parallelized, so it's a triply nested parallelization, but it's to overlap computation and communication inside the code. Plus the grid, there were some changes on the grid, which I know less about, and some experiments with OMPs as well to do some task parallelism. NEC 5000, this is again a popular code. This is a CFD code. It's a former Gordon Bell Prize winner. The work we did here was on GPU port, so we did some OpenAC and some CUDA work on this code, plus some auto-tuning, and there's also been some work on the mesh partitioning. And then OpenFOAM. OpenFOAM is very popular open source CFD code. Engineers love it because it's free. That's not the only reason. But it's very, very widely used, and we use it as well for a while. But we stopped developing on it after our review in year 2. It was decided that there is no hope for OpenFOAM ever going to the Exascale as it currently stands. And with a friendly agreement from our reviewers, we decided that we wouldn't waste any more effort on it. And I'll come back to this in a minute. So what has CRESTA achieved? So well, lots of plots, lots of graphs with scaling numbers. So here we have a plotter. This is GROMACS performance using different vector optimizations. Here we have, this is NEC 5000, looking at an open ACK version with MPI using GPUs. Down here, this is the integrated forecasting model on Titan using a huge number of GPUs and so on, and using co-arrays. This is the progress of EMLB over time. So, we have lots of pretty plots and lots of pretty graphs that we can show, but that's not really what CRESTA was all about. CRESTA was about showing that co-design and software co-design really works. So we thought long and hard about how we can actually implement and coordinate co-design within the project. And it was an important thing to get right, because if we didn't get that right, then the point of the project was just lost. So, and European projects, we all know, they all have work packages, and work packages do their work, and they have the deliverables, and it's all fine and well. But the danger with this work package structure is always that everybody just does their own thing. Everybody works towards their own goal, and everybody does their own deliverables, but the discussion between work packages is a really difficult thing to encourage. So what we created was these co-design teams that span multiple work packages. So our work was not structured 1D, it was just the work packages doing their own thing, but we had these co-design teams that span vertically across. It's quite difficult to manage. It's difficult to manage in both directions, making sure everybody does what they're meant to do, but we made it work in the end. So giving you a few examples of what we did with co-design. One, for instance, was power management. Here we used Cray working together with TUD mainly. And the Cray XC30, when it came online, we were told that it has these power measurement counters that you could read, and TUD thought that was great, so they created this ScoreP plugin for their Vampire tool that allows us to read energy and power counters, and you can overlap them with your MPI or input MP profile of your code. So this is what you get. You get a nice instant power, average power, and even accelerator instant power and average power profile for your code. So, the redder it is, the more power it uses. Another example is debugging. This is again Cray together with UCL. So the guys at UCL want to run a really large EMLB run. It runs fine on 24,000 cores. You run 49,000 cores and it crashes and it says terminated. That's extremely helpful if you've waited for 5 days in the queue. So Alinea thought this was great. Sorry, it's Alinea, not Cray. Alinea and UCL. So Alinea thought it was great because it was a real problem on real scale, and they could, really help fixing something. So they both sat together and worked on the problem, and eventually they found that it was an integer overflow somewhere in parameters, in fact, not even in the code, but in the library it used, and it was fixed. And the win-win situation is Alinea had a real use case where they could show, you could do lots of press releases and show how their tool helped solve this problem, and UCL finally got the EMLB to run beyond the petascale.
How long did it take?
How long did that take? Including queuing time, I guess, because you would have to, you'd have to rerun the problem. A couple of weeks, maybe. I mean, maybe less. There's nobody here from Alinea, or do you, maybe, Pekka, do you remember any more detail of this? No. Yeah. So, I mean, much less time than you would have.
And did they start with Alinea initially, or did they first
No, because they didn't have. I mean, they didn't see the bug, and but it was one of these things where at a meeting they said. Actually, I think we were at a project meeting in Stockholm, if I remember right, walking down the street, and they said, "Oh, my code's just crashed," and as you do, you don't have the discussion. And Alinea immediately thought, "Oh, great, a real bug, not one that we planted." And then it turned out just once you run on that core count and parameters, this one integer overflowed and division by 0 in the end, and nasty, terminated, Final co-design example. This is the integrated forecasting model. So the way they run their code, they have a forecasting scheme and a thermal radiation scheme. And this thermal radiation scheme is very expensive. So the default configuration is to run it once every forecast hour or so. And that's the picture you see here. So you run your forecasting model, you run your radiation scheme, forecasting model, and so on and so on. So what ECMWF thought about doing is simply, well, not simply, but with the help of CRE, run the radiation in parallel. So you only need to run it once every hour, but you can run it more if you want, and you also get a benefit from that. So with the help of CRE, they parallelized this, and they ran the two tasks together using hyperthreading. So the hyperthread ran the radiation model, and the main thread runs the forecasting model. So this was validated on both the XC30 and the XK7. And there's some performance benefit. The numbers vary from 3% to 25%, depending on what size of problem you run. The bigger the problem gets, the better the benefit was. So, understanding the challenges we face. So, CRESTA has shown that software co-design can work. Okay. This is driven by what we think the problems will be at Exascale, and the scale of the parallelism that you'll have to cope with. There are many challenges, okay, not just with the parallelism, but also with I/O performance, the tools, just trying to look at millions of threads in a debugger is difficult. And we have made tools advances within the project that also benefit the petascale. So the energy counters, for instance, is very nice. You can look at your MPI communication profile and you look at the heat map for your energy use, and it's very insightful. But there was a key success that we had is to create awareness of the challenges. So one example here is ECMWF had no real idea of what it means to go forward with their code. And as a result of CRESTA, in fact, they have created a scalability team that is looking at how they're going to take their code forward. I mean, you have to understand that ECMWF plan what their code will look like within the next 15 years. But they have realized that where they're going at the moment doesn't work, so they probably have to move away from FFTs, which limit them at the moment. And we have also shown that some codes like OpenFOAM will never run at the Exascale. Okay, so the story with OpenFOAM. Okay, I've talked about this many times, but a lot of time and effort was spent on OpenFOAM. We didn't give up on it easily. There's a lot of work on looking at partitioning, looking at the communication, looking at the I/O, looking at many things. And the conclusion was simply it'll never be an Exascale code in its current form. That's not to say it's a bad code, but its current form it just doesn't work. And why is that? It's mainly a problem of software engineering. Okay, so you have this massive code where you have a tiny area. It's called applications. This is nice things where you just you type in solve P and it solves your pressure field or whatever, and then that's it. I mean, tiny little code. And then you have this beast of a source folder, effectively, that has the actual implementation of the functionality. The application side is written in a sort of DSL-style programming time. So if you do A times B, the times can be whatever you want. It could be a matrix multiply, or it could be an integer multiply, or it could be two vectors, or it could be two strings, for all you know. So it's very heavily templated C++ with a beyond extreme use of operator overloading. I mean, if you can imagine overloading an operator, well, OpenFOAM does more. And it has probably very useful I/O for running on a workstation up to 64 cores. HPC, not so much. It does per process, per field, per time step I/O in their own folders. I mean, it's just doesn't work. And there's, I mean, I could go on for hours. I've given long talks on this. So the problem that you have, if you want to go in and just say, I'm going to fix the I/O, I'm going to do MPI I/O, easy, just a quick hack. That quick hack will take you 3 months to do, because all your new code has to follow the same levels of abstraction, the same style of programming that OpenFOAM already has. And it just perpetuates the program. So it's just not good. And the thing, if you want to have an OpenFOAM that works on the Exascale, you have to not use OpenFOAM and just rewrite it.
How many processes was it doing I/O roughly?
So we ran this on the CRE up to about 4,000. It's all right. But after that, it's creating directories. It's not the files, it's the creating directories that just explodes. About 8,000 cores, it just... Yeah. It just doesn't work. What next? So CRESTA's ended. As I said, it's the only project that's finished, but it's by no means dead. There are lots of new projects spun off from CRESTA. One of them, what Erwin has talked about, is Epigram, for instance. There's a project here, a little national project that looks at adding thread and instruction level parallelism to Ludwig. There's a GROMAX project. There's a SCORE E project, which looks at energy counters in SCORE P. Exaflow is led by KTH, by Erwin. This is looking at fluid flow at the Exascale. BioExcel, again led by Erwin. This is a COE. Intertwine is led by EPCC. This looks at MPI plus X, but it looks at the plus, not the MPI or the X. It looks at interoperability of programming models. And Next.io, which I'm going to talk to a little bit more on the next slide. So many of these projects are very firmly built on what CRESTA has done. And the recently announced FET HPC projects, of which Exaflow and Intertwine, Next.io, and so on, are some, we're going to take forward what we've learned in CRESTA. A lot of the partners in those projects were in CRESTA as well. And the key challenge that we've identified in CRESTA was Exascale.io. And this is what we will look at in Next.io. So this is a project led by EPCC. And we know that in the next couple of years, NV technology is going to become more and more popular. So EPCC has an €8 million project where two partners are Intel and Fujitsu, who will develop a new HPC platform using the latest technology in the NV area. And a key part, so part of the project is developing the hardware, but a key part is developing the software stack that sits on top of this. How can we actually exploit this type of technology? And we will test these strategies against real-world models of data centers and I/O. So we believe that the changes that are coming up in the non-volatile technologies are going to be transformational for HPC. But we need to get a good understanding of how we can actually exploit it. Almost finished. It's important that we make the case for Exascale. So it's very easy to take all these HPC systems and everything for granted. But we need to make sure that politicians still give us the money. So we need to make the case for why we need these systems. Okay. So we need to ask for money for hardware, which tends to be much easier than asking for money for software. Hardware, you can put a ribbon around and ask a politician to cut the ribbon. But software, that's quite difficult. So simply sticking hardware, funding hardware projects to just stick things together and say, here you go, here's a big system, that's just not enough. And none of the projects in this room have actually done that. Everybody had a set of applications they tried to validate their hardware with. But there are, unfortunately, projects like this around. So we need application drivers, we need communities that tell the politicians why it is important. We also need new maths. We need people to think about how you solve the problems we want to solve in a new way. And it's very difficult to get mathematicians excited about HPC. But if you know any mathematicians that are excited about HPC, please tell me. Please do. We need to admit to the scale of problems we face. And I think in this room we do, right? Everybody knows what the problems are. But beyond this room, I'm not so sure. So fundamentally, we need big, bold scientific problems. We need the moon race, basically, but for Exascale. Something cool to aim for. Conclusions? We have shown in CRESTA that the scale of, what the scale of the Exascale application challenge is, and we've moved some way towards making the codes better and more prepared for the Exascale challenge. We've also raised awareness, especially in places like ECMWF, where they now understand really how big the problem is they're facing and how much money they need to invest in order to go forward. And it's very, very clear that disruptive innovation is needed. Incremental changes is the ones I've shown you, for instance, those co-design examples. Those are very much incremental changes, but we need more than that. And there's also clearly a need to invest more into software. There still isn't enough money in software development. In the UK, there were 2 calls recently for software for HPC, with about 100 proposals for each call and 5 funded. So clearly there's need, but there's no money because it's just not as sexy as hardware. And we need to build the software in such a way that the hardware can actually use it. Otherwise, it's pointless. Thanks very much.
Thank you.
Thanks.